Hi, I'm Kelechi Gumbanisi, and I'm a graduate student at WPI and also a content developer for the MS4 SSA Robotics project. This is the first lesson in the mechanics module, and the subject of focus today is kinematics, the study of motion. In this lesson, we'll review linear motion and ways of describing it, such as distance, displacement, speed, and acceleration. We'll then review the same concepts for rotational motion and finally close with an important issue regarding conversion from rotational motion to linear motion. Now, many of you will find this lesson to be simplistic, and that's good. I advise you to take it as a refresher and feel free to skim through if you feel bored. However, there is substantial depth for those who are exploring these concepts for the first time. All right, let's dive in. So what is motion? And as a way to visualize this question, what is happening to the red block on the screen? You can say it's moving, yes. But what's really happening? It's changing position, right? And it's changing position along a straight line in a particular direction, which is direction towards the right, and it's moving at a particular speed. And so we see that this is a way of expressing or describing motion, talking about the distance from one point to another along a path in a particular direction and at a particular speed. So this is called linear motion because the motion is along a line. And in this particular case, it is called rectilinear motion because the line is a straight line. And so what do we know about the difference between distance and displacement? Is there a difference? So I would like you to try solving this problem. First, pause the video for as long as you need to attempt to find the solution to this problem. What is the distance covered by the robot from A to B to C to D? And also find what is the displacement. So take a few minutes, pause the video, and try to solve the problem. Okay, so let's walk through this problem together. First, what is the distance covered by the robot? So first, we know that the robot moves from A to B, then from B to C, and then finally from C to D. So from the diagram, we can see the distances that from A to B, the robot travels 12 plus 17 plus 9 meters. And from B to C, the robot travels 9 meters plus 17 meters, or 17 plus 9 meters. And then from C to D, the robot travels 17 meters, and the total of 81 meters. Now for displacement, we know that the robot is displaced along the same path, that is from A to B, B to C, and C to D. But the difference here is that we consider the direction of the displacement. So if we take left to right, which is the direction of this arrow, that is left to right, as the positive direction of motion, because the robot is moving in this direction, we take that as a positive direction for our motion, then we would say from A to B, the robot is moving by this magnitude, 12 plus 17 plus 9, in the positive direction, A to B. And then if we take B to C, the robot, which will be here at that time, going to C, will be moving from right to left. Therefore, the negative direction, which is why we have minus that magnitude, 17 plus 9. And then from C to D, the robot will be moving in the positive direction, and that will be plus the magnitude 17. And so the total would be 29 meters to the right. So from that example, what do we see as the difference between distance and displacement? Well, first of all, they had different values. The distance we calculated was 81 meters, and the displacement was 29 meters towards the right. And what do we see from these values? We see that the distance is just a magnitude, 81, whereas the displacement is both the magnitude, which is 29 meters, as well as the direction, pointing to the direction that the robot was moving in our example. And so this helps us to describe two different quantities. First is scalar. A scalar quantity is a quantity that has only a magnitude, whereas a vector quantity is a quantity that has both magnitude and direction. So here we have a car race, and what I want you to do is to determine which is the fastest car and give first to third place awards based on that. So stop and replay the video for as long as you need to determine the order of completion so that you can accurately give the award. And the hint here is to determine the speed of each car and compare them. Okay, so who won the race? Well, we can make a quick judgment by eyeballing the finish line, and you can see that the blue car comes in first, but not so sure about the green car and the red car. And so to be sure, we have to determine it mathematically. And how do we do this? One way to do it is to use a stopwatch to measure the finishing times of the cars. And so if you do that, we will have something close to these values. And so from this, how do we find the speed of the cars? Yes, the average speed of the car is the distance covered over the time taken. And if you take the length of the racetrack as L, you would get these values. So from here, we can see that the car which wins the race is the car that has the highest average speed. So speed is a measure of how fast an object is moving. But is this average speed a scalar quantity or a vector quantity? It is scalar, right? Yes, it is, because it is magnitude alone, which is 0.314 length per second. Now, the vector counterpart of speed is velocity, which is computed by taking the displacement rather than the distance over the time taken. And so the average velocity would be as follows. You have both the magnitude as well as the direction. And so we can see that the blue car is moving at 0.314 length per second in the right direction, as well as the other cars. Now, if you're observant, you would notice something interesting about this race, especially with the red car and the green car. Now, if you watch closely, you would see that the red car starts off pretty fast, but then begins to slow down, whereas the green car, which starts off slow, begins to speed up as the race goes along. Now, what does this mean, and how do we describe or measure this? And so the question is, by how much are they slowing down and speeding up? Now, if we take a point A in the race, we can calculate the average speed of the cars from the start to the point A, and then from point A to the end of the race. And that way we can see by how much the speed increased or decreased along the race. And so we can fill out this table and compare the speeds. So what I want you to do at this point is to pause the video and try to fill out this table. Okay, so in order to fill out this table, first we use a stopwatch like we did before to find out the time taking to go from start to A and then from A to the end. Now if you do that correctly, you'll get values along these lines. And then using the average speed formula that we discussed before, we can obtain these values. So what do we observe from these values we calculated? The speeds change. The red car has a high average speed from start to A, as we thought, seeing that it is the highest in this column. But then from A to end, this average speed reduces. But this is opposite for both the green car and the blue car, which have their average speeds increasing. So we see here that the average speed of the cars change, but is there a way of numerically defining by how much they have changed, how much the cars have slowed down or sped up? And yes, that is called acceleration. And acceleration, average acceleration in this case, is the change in the velocity over the time taken. And this is valid only when the acceleration is constant over the time we're considering. And there are other cases where the acceleration changes, but we'll not cover this in this lesson. But I will provide some additional resources that discuss that. So using the values we obtained in the previous slide and this formula, what I like to do is to try to complete the table to calculate the average acceleration for all three cars. And you can use these hints here to determine the right values for the velocities as you do your calculation. So pause the video now and try this out. Okay, so here's the result. And as we expected, from start to A, all the cars are speeding up. Hence you have positive values of the acceleration. And as we see that the red car has the highest average acceleration because, as we can recall, it reached the highest speed within start to A. But then from A to N, the red car slows down. The speed reduces, as we can recall, and so also here we can find that the acceleration becomes negative, and this is called deceleration. This also happens when you press the brake on your car and you are slowing down. What you're actually doing, in other words, is decelerating. Whereas with the green and the blue cars, if we can recall, the speeds increased. The speeds increased from start to A to N, and we can see that it also is consistent here with positive average accelerations in both cases. And so this is a way to summarize how we can describe motion, both distance or displacement, and velocity showing or speed showing how fast the car is moving, and then acceleration showing how fast the car's speed is changing, how fast or slow in case of acceleration or deceleration.